Okay, let's practice this problem that we've seen where we have an inner sphere. This one we're going to call a conductor, solid sphere. And then surrounding it is this shell, fairly thick, of conducting material. So this is a conductor, this is open space, just free space. This is a conductor, and outside here. And these are three-dimensional shapes. So this is a sphere with a radius R1. This is the shell has an inner radius R2 and the outer radius to the outside of the shell R3. So there's three radiuses, and we're going to put different amounts of charge on each sphere, and we're going to practice it for several situations. This is a chance for you to practice. Okay, so let's do this. Let's try a simple one first, where we make Q1 equal to 10, and Q on the outside, that Q0 is the outside shell, we'll make that 0. So that's a plus 10 and a 0. Now stop the video, draw yourself this situation, and see if you can arrange the charge and field lines for this situation. When you're done, come back and see what I've done, but don't try and do it yourself. Okay, check out what I did here. I put 10 positive charges on the outside because this is a conductor, so they can't be on the inside, they have to be on the surface. That's where I start with this sphere. And I haven't drawn the field lines yet, just so you can see the picture, but there's going to be a field line that's going to go, and it's going to pass through the conductor, so a negative charge will come to this surface. That's right on the surface. It looks like it's inside, but it's right on the surface. And there has to be 10 of them because there's going to be 10 lines, which I'll draw, that have to terminate at the surface. They can't pass through the conductor. So no matter whether this shell is charged, uncharged, charged positive, negative, or uncharged, in this situation, because there's 10 positives, there have to be 10 negatives here. That's automatic. Now, since this, in this case, is neutral, those 10 negatives that come to this surface to terminate these field lines will leave behind 10 excess positive charges. They have to go to the outside surface. And so from the outside, we see a net charge of 8, which is, in fact, the total charge inside, because it's 8. This is neutral, right? This has no excess charge on it, and that's what it looks like. Now I'm going to pause and draw the field lines. Okay, just check out what I did. I drew for the 10 positive charges that went to the surface here. There had to be 10 field lines. They can't pass through the conductor, so 10 negative charges had to come from the free electrons in the conductor to the surface to terminate the field lines. That left behind 10 positive charges, which have to go to the outside surface. And so from the outside, if you cover the whole thing, it looks like a single, the field goes out, terminates at the conductor, recontinues at the other side, and so from the outside it looks like a point charge of positive 10 right at the center. Okay, let's try another one. Okay, situation number 2. We now have negative 12 on the inside sphere, which is a conductor, and a positive 8. So I put an excess of positive 8 on this. So this has a net charge of positive 8. This has a net charge of negative 12. So I'm going to pause the video. Go ahead, see if you can do it. Do as much as you can. Don't just watch me. Try and do it yourself, and then come back and see what I did. Okay, check it out. This is a conductor. I got a negative 12. There are the negative 12 evenly distributed around the outside. I haven't drawn the field lines yet, but those field lines, they have to be 12 field lines coming in, and they can't come in from the outside because that would pass through the conductor, so we have to have 12 positive charges here. Where do the 12 positive charges come? Wherever I can get them. So notice I put 8 here. So I'll take 8 of those, but then I need another 4. So if I take 4 from the conductor, that's going to leave 4 negatives. They go to the outside surface. So notice I have 12 on the inside, because I have to for these 12 field lines, and 8 on and 4 negatives on the outside, so plus 12, negative 4 gives me the plus net charge of plus 8 on this sphere. So it all agrees with that. Now I'm going to draw the field lines. Okay, now you can see the field lines. Notice I drew 12 lines. Remembering, field lines start on positive charges, end on negative charges. That's why I have to have charges on the surface. They can't go into the conductor. They can't start in the conductor or pass through the conductor. So there are my 12 field lines. And I had these negative charges, so 4 field lines have to come in and terminate on the negative charge. So we have no field lines inside. No field lines inside. Every field line starts and ends on a positive charge. Well, these come in from someplace to end on the negative charge. We can't see where they're coming from. So notice, if you're inside the conductor, there's no field in here. If you're inside the conductor, there's no field in here. And from this point, if you look inside, what's the net charge inside? Notice, there's 12 negatives, there's 12 positives. So the net charge inside the circle I'm drawing right now is 0. That's why there's no flux or no field going through the conductor. It all satisfies Gauss's law. If you're on the outside and you look in, what do you see? You see 4 negatives, 12 positives, and 12 negatives. So the net charge inside from the outside, the net charge is a negative 4. And that's what this looks like. From the outside, the field looks like a point charge of negative 4 right at the center. Does that make sense? Yes. Because the total charge inside is a negative 12 and a plus 8. That adds to a negative 4. So everything checks out. This is what you should have. Okay, I'm going to pause and go into the final situation. Okay, here's a challenging one. So this time we're going to make this an insulating sphere. And we're going to put 8 charges. It's not a conductor, so we can put the charges evenly, uniformly distributed throughout the sphere. This is still a conductor. We're going to put a negative charge of 20 on there. So first thing is arrange the charges like we've been practicing. And then once we've done that, we're going to come back and calculate the electric field at these points, 5 centimeters out, 15 centimeters, 25 and 40 centimeters from the center. And so this has a radius of 10. The inner radius of the shell is 20, and the outer radius is 30, right? So 10, 20, 30. So this has a thickness of 10 going from 20 to 30. All right, so do the charge distribution and then come back and see if you get it right. Okay, check your charge distribution first before I draw the field line. So the 8 that I was given, I distributed them evenly over the sphere. That means I have to have 8 here, right? those 8 field lines that I'm going to draw have to terminate without going through this conductor, so I have to have 8 negatives there. But in this case, I was given 20 negatives, so I don't have to steal any from the conductor. I'll put 8 of them here. That leaves 12 left over to be on the outside. And so if we look at the outside, we see a charge of negative 12 plus, also another negative 8 plus 8. So the net charge inside is a negative 12. And that's what I'll get, 12 field lines going in. Okay, pause and draw the field line. Okay, notice what the field looks like. So if you drew the field lines from the surface, I probably won't complain, but they do come from the inside because the charges are inside. So the field lines are coming from these 8 charges, and they're all terminating at the surface because this is a conductor. Remember, this is not a conductor. So they terminate at the surface. And then field lines come in from far away, and 12 field lines. These should be evenly drawn. It's kind of sloppy. But the 12 field lines come in. So if we're out here, what do we see? We see 12 field lines coming in as if, identical to, if there were a net charge of negative 12 at the center, and we notice that is the net charge inside from the outside. If you count all the charges, you end up with a negative 12. Okay, last step is we want to calculate the electric field at these 4 points. So some point inside the insulator, 5 centimeters out, there's going to be a point between these 2 objects, 15 centimeters out. We're going to calculate the field at 25, which is in the middle of this, and then the field out here, somewhere out here at 40. So see if you can do that, and then I'll show you what that looks like when you come back. Okay, I added this. So in order to do the calculation, you do know this is plus 8 and minus 20 watt. This is nanocoulombs. So I'm going to, so anyway, if you didn't know that, go back and do the calculations. Don't look at what I did, and see if you can do it on your own. It's much better practice if you do it on your own. Anyway, once you're back, having tried, you can check your answers. So I'm going to do it from the outside coming in. So the first one I did was the E40 out here. So when we're out here, the field, the net charge inside is a negative 12. Notice there's 12 field lines going in. When you're out here, the field looks identical to the field of a charge of negative 12 at the center. And so I just use the usual point charge equation because a spherical charge distribution behaves like a point charge. And there's my K, and there's my net charge of 12. I didn't put the negative sign because I just want the absolute value. So 9 times 10 to the 9th, 12 times, 12 times 10 to the minus 9, so I'm not going to, the minus 9 and the 9 are going to cancel, 0.4, so all I'm going to do is multiply 9 times 12 divided by 0.4 squared. Notice I showed you the units cancellation, and anyway, I end up with 675 newtons per coulomb. When we get to E25, that's inside the conductor, and so that's 0. No calculation is necessary. And it's also consistent with what we know, because from this point, if we look inside, we see a negative 8 and a positive 8. So from this point, there's no field lines because there's no net charge inside, consistent with Gauss's law. Okay, when we're in at 15, the field is 8 lines going out. It's the field of the charge inside, the plus 8. This field here in this space looks identical to a point charge of plus 8 at the center. So we use that equation. K Q over R squared. So the K is 9, the Q inside is 8, the distance is 0.15 meters. I show the units cancellation, I do the calculation, I get this result. The hardest one is when we're inside the insulator. Now if this were a conductor and we're inside, it would be 0, but it's an insulator. And so when we're at 5 centimeters, the scale is a little small here. When we're at 5 centimeters, can I expand this? Let me see. Let me just bring this in for a minute. So when we're at 5 centimeters, whoops, we're halfway out. Maybe that doesn't. Whoops. I'll bring it back. It's a little clumsy. So this is the tricky part. If you're halfway out, you don't, the thing that's going to be inside that little sphere, let's go back to this. If we take a little sphere, which is radius 5, you have to think about volume. That sphere of radius 5 has only 1/8 the volume of a sphere of radius 10. And that's because the volume of a sphere whoops, let me pause. Okay, let's try that again. The volume of a sphere is 4/3 pi r cubed. So that means if the radius is half, 5 is half of 10, then the volume of that inner smaller sphere is only 1/8. I don't want to spend too much time on that. If you don't follow that, ask me about it. And so that's why when I calculate E5, at 5 centimeters out, the amount of charge inside is 1/8 the 8. So this 8 here, but inside that little sphere inside, there's only going to be 1/8 of the charge. So I've got 8, the total charge divided by 8, which is 1. And the 10 to the 9, 10 to the minus 9 cancel as usual. So I have 9 times 1 divided by 0.05. I get this result. Okay, we're done.